Hey everybody, it's Ripley back again. Today we're going to talk about another application of the definite integral, which is volumes of solids. So we already talked about the area. I'm gonna keep this one simple today. We're going to deal with the square root of x. So I've got y equals root x. And we already know how to find the area under the curve, right? If I want to find the area, it's pretty simple. Let's make it interesting. Let's just go from, I don't know, 0 to 9. So we'll make this 9, we'll make this guy 0. If I want to find the area, I simply take the integral from 0 to 9 of the square root of x dx, and this is equal to 2/3 x to the 3/2 from 0 to 9, which is equal to 2/3 of 9 to the 3/2 minus 0, right? Because you stick a 0 in and off you go. Square root of 9 is 3. 3 cubed is 27 divided by 3. 27 divided by 3 is 9, so this guy appears to be 18. I'll buy that. Let me double check that. We got 3 cubed, 3 squared. Yeah, and we're good. All right. However, I want you to think about something. What if we were to take this guy right here and take this region? In a lot of textbooks, you'll see this as a fancy little script R. It's written kind of like that. So I'm going to call this the region. All right, I'm going to change colors here really quickly. If I call this guy in here the region, and I want to rotate it through 360 degrees. So this is just a flat region in the plane, and I rotate that thing through 360 degrees. What would that look like? Can you see what it would look like? Whoops. Oh, terribly wrong. Do you agree what it would look like is kind of like half of a watermelon, right? If we took the water, or half of a football, because what would happen is I would get little discs, right, that would come through, and I'm going to use a computer algebra system. I'm going to use Wolfram here in a sec to show you. I would get these little discs, right, as I folded this out. I don't know if you've ever had, like my parents had these, like Halloween or Christmas decorations that lay flat. They're like crepe paper. And then you open them up and spun them through 360 degrees, and what you got was a solid. All right, so the foundation for this is actually quite simple. I'm gonna pop over to a little demonstration project here. And I'm gonna show you, check this out. We got the square root of x, which is really nice, okay? I'm going to show you what this would actually look like. So in this case, what we have are these discs, and they could kind of look like hockey pucks or clearly cylinders, right? And in this case, it doesn't say where I'm going from and to. It doesn't really matter. However, oh, I guess it does go from 0 to 4. What if we go from 0? Let's go from 0 to 9 like I have it. Let's go 0 to close enough. Perfect. All right, now you can see as I rotate this, it's kind of hard to, you see the function back in there? It's this little faded line right here. But if I take the number of these segments, so instead of, let's put that there, instead of my awful drawing, what this is, this has a number of segments of 2. If I let the number of segments increase, watch what happens. That's pretty awesome, huh? Right? So this is 28 segments, right? You can see like the first 2 that we started with, but as we add, they sort of crunch down, and we end up with that sort of half of a football looking thing. I guess it looks a little more conical, but it doesn't matter. Now look at the solid of revolution. This one's pretty cool. As I wrap this guy, through 360 degrees, can you see it in there? That's pretty amazing, huh? God, I love technology. It's a good thing because I got a PhD in it, right? All right, boom, look at that. See, as I increase, even I could, oh, wow, that's pretty cool. Look at this. Oh, sorry, I'm just sitting here playing with this thing. So a couple of things that I want you to notice is first, that each one of these segments, as they call it, looks like a disc or a cylinder. That's the most important thing. That means when I take something and when I take a rectangle, which we're used to dealing with, and I wrap it through 360 degrees, I get one of these little cylindrical looking things. Okay? Now, let's go back. Hold on. I'm going to shrink this guy down. And what I'm going to do is I'm going to go back to our idea about what I refer to as a slice of action. So here's a slice of action right here. Whoops. That's a crazy looking slice of action. Now I want you to notice a few things about it. Okay, first and foremost, we're going to center this slice of action at some x sub I. Maybe I should use a different color. Yeah, it doesn't matter. All right, let me erase that little pooch we got right there. First things first, we've got, this is really important. we've got it centered at some x sub I. But way more importantly, if you think about the thickness of that slice of action, it's got a delta x. Now, because it's got a delta x, every single thing that we do has got to deal with values of x. Now, do you agree that if I rotated that through 360 degrees, what I would get is I would get this hockey puck looking cylinder that looks like that. Now, this would be delta x thick, right? This guy right here would be delta x, and the distance from here to here would be f of x sub I, because the distance from here to here is f of x sub I. So basically, f of x sub I becomes the radius. This is the radius at this little ith subinterval. Now, at this point, it's really simple, especially if you want to find the volume of this solid. So the volume of the ith interval, in other words, the volume that my little slice of action created, is just going to be pi times r sub I squared times h sub I, which in this case is just pi times f of x sub I, that squared, because that's the radius, right? That's squared, and then times, what's the h? What's always the h for one of these little slices of action? Well, it's delta x. That's easy. It's pi r squared h. It's pi f of x sub I. Now, you maybe, or f of x sub I squared times delta x, right? Easy peasy. But if I want the overall volume, well, if only we had a mechanism by which we could add up an infinite number of infinitely thin rectangles. Oh, our lives would be so good. Well, it's easy. I just go pi, right? I'm going to take the integral. That's the mechanism, isn't it? I take the integral from 0 to 9. Why? Because that is where the action is taking place, and that becomes really, really important. Okay? Excuse me. So I go from 0 to 9. Everything's got to be in terms of x's. So what's f of x? Well, it's the square root of x, right? I guess I could rewrite this as pi times the square root of x sub I squared times delta x, correct? And this thing turns into, well, the square root of x squared is just going to be x, and this is going to be dx. This turns into pi times x squared from 0 to 9. Whoops, x squared halves from 0 to 9. And this is what? 81 pi halves, right? I just did that in my head. You're going to have to forgive me. Sometimes I work a little bit quickly. Well, that's the easiest thing ever. Let's look at one more of these little guys. How about, where was it? What if I change my, let's change my function. All right, let's just change my function to x. Yeah, as you would expect, let's turn these back down. Let's turn these back down. As you would expect, it's hard to see, but you can see, it kind of bums me out that it's difficult to see the function. You can see just a little bit of the function sticking in there. If I turn the number of segments up, that would be the number of disks. That's why this is called the disk method. Up, it starts to become more conical, and then if I do the actual solid revolution, then I end up with a cone. Oh, just for giggles, let's throw in one of these guys, shall we? Let's do that. Whoa, that one's cool. Look at that. That thing's amazing. All right, let's turn the number of segments down again so we can sort of see how, I don't know why it's so small. Even if I make it big, I think it's just, look at that though, that's amazing. Love it. I don't know, look at that. Look at that crazy sort of, I don't know, polygonal thing around the edges. I don't know what, that must be a glitch. All right, enough of this business. So that's how disks work. Super simple, not a whole lot to it. What if I wanted to find the volume? What was that? X, right? If I wanted to find the volume of that cone. So I'm going to change colors again. We're going to do this super quick. Whoop, whoop. All right, I've got y equals x. This is y equals x, and I want to find the volume. Let's see. This is going to be let's just do 5 this time instead of out to 9. I use 9 because the square, in case we had to figure out square roots. Okay, anyway, so when I take this, if I take this out, I just showed you with that little demonstration, I get, right, what do I get? As I wrap this thing through 360 degrees, I'm going to end up with a thing that's just basically cone, right? It's going to be a cone. This is kind of cool. It's going to be a cone that's going to be 5 high. Whoops, 5 high. And if you think about it, what's the radius going to be? Well, it's going to be 5 as well. Now, we already know that the volume of a cone is equal to pi thirds r squared times h. So in this case, it's going to be pi thirds times 5 squared times 5, which is 125 pi thirds. But let's prove that with our good friend, the disk method. All right, draw your slice of action. Always label the thickness of your slice of action. In this case, that's going to be delta x. And this height is always going to be x sub I. Remember, we anchor this thing at some x sub I. Since y equals x, we're there. So the v sub I is going to be pi times f of x sub I squared, right? Pi r squared, because that's the volume of a cylinder, just in review. So this is going to be x sub I squared times the thickness, which is always going to be delta x, or delta y, depending on if we have a function of x or a function of y. We'll discuss that a little bit further here in the future. So this is going to be volume is equal to pi times the integral from 0 to 5, excuse me, of x squared dx. And this guy turns into pi times x cubed thirds from 0 to 5. And if you think about it, I'll actually do this one out because I've been a little bit lazy. This is going to be 5 cubed thirds minus 0, which is 125 pi thirds, which is awesome. Okay, so in general, all I do if I want to figure out the volume of a solid, if I want the v sub ith, right? If I'm using disks, now we got to be careful here. This is going to change here in a second. I don't know why I just flipped over there. I know that the volume is simply going to be pi times the integral from a to b of some radius squared. This is for the disks. Radius squared dx. Now notice, in both of these cases, there is no hole between the action and the axis of rotation. Right? There's all of the action spins around the x-axis. So in other words, this slice of action just sort of rotates around itself to produce this cylinder. Now what we're going to talk about next is the washer method. I'll meet you over on the other page here in just a sec. And that's the washer method. And I'll kind of show you what happens with that, and I'll give you a good example of how it plays out. All right, I'll see you in a sec. Okay, now let's talk about volumes by washers. So in a washer situation, now let's think about what a washer is. Isn't it a disc, a small disc, right? It's actually more like a compact disc, but with a hole cut out of the middle, right? Like you would have this little down here. That's a washer. So what we're doing in volumes by washers is we're taking some function f of x and another function g of x. I don't know what happened with that x. And I'm going from A to B, and I'm going to rotate that through 360 degrees. Now, I am an awful artist. You probably already realized that. So I'm going to utilize Wolfram to demonstrate what that looks like. All right, so in this case, we've got this region. This thing looks semi-sinusoidal of some sort. Ooh, that's a lot of alliteration. And then this is linear, and this is going to be the axis of rotation. I don't know why they didn't put the axis of rotation somewhere else, but it doesn't really matter, okay? And then what we're going to do is we're going to rotate it and watch what happens. As it rotates, you see what you get. That's pretty cool, huh? Oops, keep going. Come on now, don't be shy. As you rotate, you see what you get. You get each one of these little segments. Now the whole thing looks kind of like an urn, doesn't it? But each one of the little segments creates a disc. So just look at the face. I think I can rotate it. Yeah, just look at the face. There is your disc. Oh, sorry, there is your washer. Let's try that again. And look inside. You can see a whole bunch of washers. These are basically the centers of the washers. For those of you that don't know what a washer is, it kind of looks like that thing. Now, apparently, the computer has a hard time distinguishing between circular and polygonal, but that's okay. We'll forgive them. This is still a really cool. Oh, what's going on? Let's get rid of that. Hold on. I want to see if I. Whoa. I want to see if I can. Oh, wow. Oh, okay, let's try that again. Here we go. Ugh, I love technology until I don't. Let's move. Doesn't want to let me do anything. That's very interesting. Wow. Okay, doesn't matter. We can get rid of it. That's odd. I kind of wanted to show you the second region. Wow, I just up and locked this thing up, didn't I? Well, good to know. That's why I couldn't get to it. That's really strange. All right, so anyway, here's what I want to show you is just like always, what we're going to do is we're going to create a slice of action. I'm having all kinds of technology issues, aren't I? I'm going to create a slice of action. Here's my slice of action. It's in the region. This guy right here is, here's my fancy script. I'm pretty good at those. And then this is going to be my x of I. Right? Now, I'm going around y equals 0 or the x-axis, true? So what I have to do, for those of you that know what a lathe is, what I have to do is I'm going to create the volume. I'm going to create the volume of the ith segment by the ith slice of action. I prefer to do that by looking at, I'm going to make a big disk with the outside function first. Oh, I'm being a little bit lazy. We got to put a delta x there, don't we? Because that tells me what all my limits are, and I got to really pay attention to that. So let's change colors here real quick. Do you agree that if I were to go, there we go, if I were to take the outside edge of this slice of action through 360 degrees, it would behave just like a disk. In other words, if I completely disregarded this g of x part and just called this f of x sub I, what I would get is just a big disk. I would get pi times, let's go back to here, pi times f of x sub I, that squared, times delta x, right? Because the thickness is, delta x is the thickness of the interval, which gives me, it would basically be this cylinder without the middle cored out. Think of it as coring. However, there's a problem. That would give me way too much volume. So what I do need to do is I got to scrape out the middle. And how do I scrape something out mathematically? Well, I subtract. So think of this guy as being a big radius or a big distance from my axis of rotation out to the edge of the action. And this guy as being, I'll put a little sub I there, as being my little radius. And we know that the little radius in this case is just g of x sub I. So I make a big cylinder and then I carve out the little cylinder, g of x sub I squared, right? This guy right in here would have volume of pi times g of x sub I squared times delta x as well. So if I wanted the overall volume, I'd simply add up an infinite number of infinitely thin slices of this action, which would just be, notice pi is common to both, so I can factor it out. I would take the integral from a to b of f of x squared minus g of x squared dx. Now, so a way that you'll see this very often in textbooks is you'll see this as pi times the integral from a to b of f of x, or excuse me, not f of x, but of big R, like think of it as a big radius. Excuse me, big R of x squared minus little r of x squared. So if you see that notation, don't panic. It's not a big deal. Okay, now here's what we're going to do. I'm going to take two functions, and I'm going to find this part right here is, this is going to take a little bit, but I think it'll be really instructive and really helpful for you. All right, I'm going to take two functions. I'm going to find the area in between those functions. Let's let f of x equal x squared, and I'm going to let g of x equal, what do we want this to equal? 2x. So we'll do a quick little sketch right here. And then I'm going to wrap this, let's go 2x. I need that a little bigger, don't I? Because I'm going to exaggerate. Remember how I said when you're dealing with these, try to exaggerate what's going on? So I'm going to do this. I know that looks more like x, but we're not worried about it. And then here comes x squared. So this guy right here is y equals x squared. And this guy right here is y. Whoops. What the heck, Ripley? Sorry, try that again. Y equals 2x. And this guy right here is y equals x squared. Now, just like always, the most important thing that I'm going to do is I'm going to draw a big old slice of action right here. That's going to be my slice of action, and I'm going to have a delta x right there. Now, I'm actually going to take this thing around 6 different axes. But first, let's find the area between, shall we? How do I find the area of the region bounded by these two curves. That should be relatively easy to see. Where do they intersect? Is it relatively obvious that this is 0, 0, and that this is, what, 4, 2, or 2, 4? That's 2, 4, right? All right, so the area, excuse me, is going to be the integral from 0 to 2, because I got a delta x right there. You may say, Ripley, are we ever going to do anything with functions of y? Well, just simmer down now. Relax. The upper function is 2x. The bottom function is x squared. And I got dx, and this guy is going to be x squared minus x cubed thirds. From 0 to 2, I plug 0 in, everything's going to disappear, and I get 4 minus 8 thirds, which is 4 thirds, right? 12 thirds minus 8 thirds is 4 thirds. Easy, done. Now, here's what we're going to do. We're going to set up, but we're not going to solve. We're going to set up a bunch of integrals when we take this region and we wrap it around different axes, okay? So the first axis, let's keep it simple. We're going to go the x-axis. We're going to set up, but not solve. Volume is equal to, now here we go. I'm going to get a little crazy, all right? Hopefully you see if I'm going around the x-axis. Now, I'm going to give you a mnemonic device right now, and you're going to think it's silly, and you're going to think I'm stupid, but trust me, it's going to be very helpful for you. The mnemonic is this. Notice that this slice of action is perpendicular to the axis of rotation in this case. So we're going to use either disks or washers. So what, pray tell, you may ask, Ripley, is this mnemonic you speak of? Well, if you are perpendicular to the axis of rotation, you're going to use disks or washers. If your slice of action is perpendicular to your axis of rotation, you're going to use disks or washers, because really washers is just an extension of disks, right? Okay, so enough said. You're like, well, Ripley, what other method is there? Well, there's something called shells, and we'll talk about that actually in the next lesson, but I want to sort of plant the seed and drive you guys crazy at the same time. All right, so let's try this. I know that since I'm going around the x-axis, I know that this is my big R, and this is my little r, so my volume is going to be pi times the integral from what to what? Well, that delta x tells me everything is in terms of x's. I can't have anything except values of x. So the value of x on the left-hand side of the region is 0. The value of x on the right-hand side is 2. And then it's just big radius, which is 2x squared, right? I square these, remember, right here, minus the little radius, which is x squared, dx. I'm done. Easy. Easy as falling in love, as they say. Okay? Nothing to it. I told you, we're just going to set them up. Now, how about if I go around y equals -2? What's that going to do? Well, let's draw y equals -2 down here. We're just going to sketch it. Y equals -2. Now, instead, let's go back to here. Instead of these guys, from the distance from the x-axis up to the edge of the action, and the upper edge, and the x-axis up to the lower edge, what I'm doing is my big R is now that guy, and my little r is now that guy. So what does that do to my integral? Well, the distance from the x-axis up to the edge is still 2x, but the distance from here to here is always 2. Now you may say, Ripley, whoa, why aren't we putting -2 in there? Well, because distances are always positive. So the volume is going to be, now follow along, pi times, now again, where is the action taking place from and to? Well, it's from 0 to 2 again. It never changes on this, right? That's where my slices of action are, from 0 to 2. No matter what I do, that's where they're always going to be. All right, and then what do I have? My outside radius is going to be 2x plus 2, right? That's the distance from here to here. Always, from 0 to 2, it's always 2x plus 2, no matter where my slice of action is, right? Even if it were up here, it would still be 2x plus 2, all right? And then I square it, because my outside radius, minus my inside radius, which is just x squared plus 2, and I square that, and then I've got my dx, and I'm done. Now, one last. How about this? How about, well, one last here. How about y equals 10? And this is the one that really screws students up. And I'm going to need to do a little bit of erasing, which could jack up my, let's get rid of all of this. Slice of action still remains the same, but let's think about what happens here. All right, now let's change colors too so we don't get confused about the red. Here is y equals 10. Here's my slice of action. The thickness is still delta x. Do you agree that the slice of action, or excuse me, the big radius is always the distance from the axis of rotation to the outside edge of the region? So it's going to be this guy right here. The little radius is the distance from the axis of rotation to this little inside edge, and then there's this hole. Now, one thing that I always tell my students is that you can always tell if you're using discs or washers on a region because is there a hole between the axis and the action? Is there a hole between the action and the axis of rotation? And it should be relatively obvious that in all of these cases there has been. Now, remember back here when we did the square root of x, notice no hole. Here was my slice of action. Here was my axis of rotation, and there wasn't a hole. So that's a good thing to sort of remember. Sorry, I'm getting ahead of myself. All right, so let's do y equals 10. Now, outside, well, same thing. Since we're using shells, or excuse me, since we're using washers, I know it's going to be pi times the integral from 0 to 2. The action is still taking place from 0 to 2. Hopefully you're getting as bored of that as I am. Now, let's look at this. I know the distance from here to here is always 10. Distance from here to here is always 10. And the distance from here to here is always y equals x squared, isn't it? Right? From the horizontal line up to the function. So if this distance from here to here is always 10, and this distance from here to here is always y equals x squared, then guess what? The big radius is always going to be 10 minus x squared. And then I square that. Let's extend that. What's the little radius? Well, the distance from here to here is always 10, and the distance from here, where am I going to put this? The distance from here to here, this what used to be an outside edge is now an inside edge for y equals 10, is equal to y equals 2x, right? True? So now think about that. What's the inside radius? Isn't it going to be 10 minus 2x? Minus 2x squared and dx. And I'm done. Okay? Now, I'm going to change it up here in just a sec. But I want to make a couple comments. You've got to be really careful when you're doing these. The errors that you, as a relative newbie with these, are going to make, excuse me, there's really only two. As long as you pay attention to everything, as long as there's no brain farts in there, which happen, the errors that you're going to make because you get confused is you're going to flip these, but if you flip them, the volume will be negative, and volume can never be negative. So that's a nice little hint. The other error that's a little more egregious, and it happens a little more often, is instead of capital R squared minus little r squared, what students will do is they'll go capital R minus little r squared, and that is bad. That is bad. That's really bad. Okay, now I'm going to stumble over here, and we're going to keep going with this region, but I'm going to redraw it because that's just a cluster over there. Let's do. I'm going to make it even a little bigger this time because this is where it gets a little crazy. Oh, no. I need that vertical line a little moved over because I'm going to do some stuff here. All right, let's move it over here. And then I've got my y equals x squared. Wow, super exaggerated. Oh, man. Y equals x squared. And then I've got my y equals 2x. Try and pretty this up a little bit. Right there. Boom. So that's awful. This guy's y equals x squared. And this guy's y equals 2x. So we're still dealing with the same thing. Remember, we've still got the point 2, 4. And I've got the point 0, 0. Now, here's what I want to do. I want to take this guy around. I want to take it around the y-axis now. Y-axis. A little lag there. Now think about this. Here's the problem. If I'm going to use discs or washers, and I need my slice of action to be perpendicular to the, I know it's awful, but perpendicular to the axis of rotation, then I'm going to have to draw a slice of action that looks like that. True? And if that is my slice of action, then the thickness of said slice of action is going to be delta y, which now tells me that everything has to be in terms of y. I need functions of y, not functions of x. So what that means is I have to rewrite this as x equals root y. And I have to rewrite this as x equals y. Whoops. That doesn't want to write up there. Y halves. Otherwise, I can't do it. So now let's look at it. It shouldn't be too bad. If I want the volume of the solid, everything is in terms of y. So we're still going to do the same thing. Notice there is still a hole between the action and the axis of rotation. My outside radius, let's change that again. My outside radius is going to be here. My inside radius is going to be here. So my volume of my solid is going to be pi times the integral from where to where? Where is my action taking place now? Remember, everything's got to be in terms of y's. Y starts at 0 and it finishes at 4. Outside radius, farthest to the right, is root y, and I square it, minus the inside radius, which is y halves. And I square that, and I'm done. Now, the nice thing about these types of problems is the integrals that you're actually taking, because you're going to have to take a lot of them by hand, the integrals that you're actually taking are pretty easy to do. If I open this thing up, if I expand this, this would just be the integral from 0 to 4 of y minus y squared fourths. That's super easy. That's kind of a no-brainer, right? All right, so we got the y-axis. Now, what if I want to go around, let's go x equals -1. I've sort of got a little dash mark here anyway that I can use. Now, what happens? Let's go back over here. Just like before, what happens is my big radius gets extended to there, as does my little radius. Well, how do I deal with that? Well, again, we don't panic. All we do is we got volume equals pi times the integral. Action still takes place from 1 to 4, or from 0 to 4, excuse me. The distance, let's do big radius first. The distance, this is, by the way, x equals -1. The distance from here to here is always 1. It's a distance. The distance from here to here is always root y. So the big radius is always going to be 1 plus root y. And I square that. That could be expanded algebraically if we needed to. Minus the inside radius, which is 1 plus y halves. And I square that guy, and I slap a dy on there. Oh, wow. Holy smokes, did I put a dx up here? Someone needs to yell at me, because I'm sure there's a great hue and cry and trolling on the internets and the webby spaces. Ripley, you screwed up. I'm glad I caught that. It just took me a minute. Just everybody relax. For gosh sakes, you guys are so angry. Okay, now let's do the same thing that we did before. How about x equals 10? I don't want to do 10. Let's do 5. All right, so x equals 5 lives out here. Here's my x equals 5. Clearly not drawn to scale. Now, big radius. This is my big radius. I tell my students in my class, for them to receive full credit, I want a slice of action and a sketch on everything that they do. And I'm going to do this one in purple. All right? So I want to see all of this. These are starting to get a little bit confusing. So let's get rid of this big radius over here. Just sort of get it out of our way so we're not confused by it. There's a lot going on. That's the hardest part about teaching this is you want to be able to do everything so students can see it on one screen, but that can get really confusing. All right, same thing as before. Distance from here to here is always y halves. Distance from here to here is always 5. So the distance from here to here, well, let's go volume, pi, integral, 0 to 4, just like before. The distance of this r sub I, little big radius, little radius, I know I didn't use those before, but hopefully you'll forgive me, is just going to be 5 minus y halves. So it's 5 minus y halves squared, right? This is always y halves, this is always 5, so this is always 5 minus y halves. Minus, now I have to carve out the middle, I have to core it. I've never used core before, that's kind of cool. This is always 5. This distance, however, is always, root y. So if I want the little radius, I simply go 5 minus root y squared dy. And I'm done. That's it. That is discs. Discs. These are discs. Right? And these are washers. How can I tell? because there's a hole between the action and the axis of rotation. I know that I'm using discs and washers in all cases because my slice of action is perpendicular to the axis of rotation. When I was going around horizontal axes, then my slice of action was vertical. When I was going around vertical axes, then my slice of action was horizontal. How did that change things? When it was horizontal, everything was in terms of y, unless you screw up like I did. And when I went around, when my slice of action is vertical, then everything is in terms of x's. The trick is to draw your slice of action. Then everything takes care of itself. If you try to memorize all this, it's going to get too confusing. You end up in coin flip situations, and that can really screw you up. All right, there's one more thing that we need to cover in this section because a lot of textbooks cram all of this in, all right? I'll meet you on the next page and we'll get that done. All right, I'll see you in a second. Okay, the last thing that we're going to cover in this video, and I know this video is getting long, but this doesn't take very long, excuse me, is going to be volumes of solids of known cross sections. Now, you can get really, really wrapped up in how this gets written. All right, so I'm gonna speak it, and then you're gonna have to take some notes on it. I'll write up like maybe one problem or something like this. The way that this works is you've got volumes of solids where you know what the cross section looks like. I need to make sure that you understand in the case of these types of problems, there is no rotation. You are not rotating anything around an axis, so don't do it. All right, don't ever do it. Now, what if, here's what I'm saying. Let's take a slice of action. Just like always, just like always. I know this is 0, 0, and this is 2, 4, and this guy here is y equals x squared, and this is y equals 2x, and we're good. But what if the base of a solid that we knew was a square, let's keep that simple, was in the region, because this down here is our region, just like always, was in the region, but the square itself protruded out of the plane, sort of at us. So in other words, what we would get is sort of this square coming out at us. Down here, we'd have smaller squares coming out at us. I'm decent at drawing these, not fabulous, but decent, right? And then these guys, now notice what I'm drawing is these guys coming out at you. Now, what would that look like? Well, the base of the solid sort of looks like a banana, right? So it kind of does. But what would happen as I came out is this thing would have ridges on it. Now, I'm going to change colors, and I'm going to draw something different. Let's see if you can see through what I've already drawn. So, wait. Blue color was squares with base in the region. Now, you'll often see this as perpendicular to x-axis. Notice, again, our slice of action is perpendicular to the x-axis, as are the squares. The squares themselves are perpendicular to the x-axis. And there's a little applet I'm going to show you as well. How about semicircles? Semicircles with diameter in the region and perpendicular to x-axis. Like, what would those look like? Well, let's change colors. How about purple? Now, instead of having squares coming out at you from the region, I would have semicircles. Now, this is really going to look like a banana that's been sort of sliced lengthwise, true? Coming out at you. Semicircles, boom, boom. All right, let's see. Let's do one more. Let's do triangles. And I know this is going to be god-awful by the time we're done, but let's do orange. Let's do triangles with base in the region and then perpendicular to x-axis. Okay, triangles would say, let's make them equilateral. Okay, so again, now I would have, whoop, here's my slice of action, and out would pop these triangles, whoop, whoop, just like that. And I know I should probably redraw these to get all the triangles, but I think it's almost easier to see what they look like if you put them right over the top of one another. And then I have this little handy applet called Wolfram. Pow! Look at this. Okay, now, Love this applet. So look close. What we have is we've got a region. This is the base region. This is in the xy plane. And then what we have is perpendicular to the x-axis, we have semicircles. So if you look at this object, it almost looks like an urn, doesn't it? Isn't that awesome? So here's my base. You can see the base. Notice they look the same right there. And here are the semicircles coming out at you, coming out in 3D. That's pretty neat, huh? Now, what if they weren't semicircles? What if they were equilateral triangles? Pow! Now look at that. Wait, whoa, whoa. Oh, I did it again. Oh, man, come on. Okay, hold on. Let's see if I can, why did that do that? I need to stop using my, let's see if I can change that. Yeah, I locked it up. So we'll get rid of that. All right. Dang it. I'll meet you guys back here in just a sec because I got to make this thing work. I want you to see if you, okay, let's try that again. Notice equilateral triangles. Here's my base. I don't know what it is about that. When I use the stylus, it gets crazy. How about squares? Bam. Look at that. Base down here, squares popping out at you. It's a lot easier to see, isn't it? We already did semicircles. What if we had a mixed? Now notice here's my base region. Let's see if we can find my base region in all of this because that can get a little confusing. Oh, it kind of looks like that's my base region, doesn't it? Because it's flat. I'm not even going to try and spin it. That'll drive me insane. Oh, yeah. So here's my squares. So my squares are coming out of the base region. They just have it flipped by default. How about equilateral triangles? Now we can see, yeah, that's better. Base region there. Wow, is that really? Why would they do that to me? They must hate teachers. All right, now we got our base region. Do we? Wait, kind of. Ugh, yeah, this thing's flipped around. Anyway, triangles popping out at us. There's that side right there. Notice how this side is sort of curvy, but this side is flat. This is flat by virtue of this side right here. How about semicircles? Semicircles is always the easiest way to sort of see what you're looking at. That's neat, huh? That pops right out at us. And then my base region is underneath, but when I flip it around to try and see it, it gets transposed. That's pretty cool. Look at the semicircles right there. That one last. Let's do rectangles. Pow. Curved. Looks just like that. Rectangles coming out at us. Okay, enough. We got enough. All right, what I'm going to do is, I'm going to do, let's do squares. We'll do semis. That's perfect. I'm going to do triangles, but I'm going to make these a little bit easier on myself because I know you guys are probably tired of listening to me talk. I'm going to find the volume of all of these solids coming out of this region. So first things first, let's do squares. Now, I'm going to show you how I do this, how I do it with my kids in class. So squares. Now, you've got 4 steps every single time. The first thing that I have them do is take the area of a square. You're like, Ripley, seriously? Area of a square. Now, well. That's going to be my slice of action. So everything from this point hence is in black. So we know what we're doing. All right, we're going to have a little slice of action. Area of a square is side squared. Wow, that was really hard. And then we know that my square comes out just like that, right? So the area of a square is side squared, right? Side squared. Now the area of the ith square, now we're jumping into this equation. Well, a side of this square, into this region, a side of this square has a base of length 2x sub I minus x squared sub I, right? That's the distance from here to here, is 2x sub I minus x sub I squared, right? That's that length. So if I want the area of that thing, I need to square it, right? Think of this as being S. So I square it. Well, that was hard. V sub I, if I want to make volume, well, what do I do? How do I create that volume? Well, remember, every slice of action has a delta X. So that means that this volume comes out like this and out like that. Ooh, that's a pretty good little drawing right there. I'll take it. And it looks like that. Right? It's like a deck of cards almost is what it looks like. So V sub I, the only thing that you have to do to get from A sub I to V sub I is take 2x sub I minus x sub I squared times delta x, and guess what? You have your volume. Now, that's just the volume of this guy. This is V sub I. If I want the volume of the entire thing, then I simply do what? I add up an infinite number of infinitely thin slices. Oh, that's right. There's this magical thing called an integral. So I take the integral from where to where? Hopefully you see 0 to 2 because that's a delta x. And this is 2x minus x squared dx. And I'm done. Wow, that was hard. Okay, let's do semis. Nope, I need to change colors though. And I'm going to change where my delta x and all that, or where my slice of action is. So now we're going to do semicircles. Semicircle. So the semicircle, brain's not working today. I know that the area of a semicircle is pi r squared halves. First step every time. Now I'm going to move my slice of action. Here, down here is going to be my slice of action this time, because I've already got a little semicircle drawn out here, right? Area of my semicircle, easy peasy, pi r squared halves. Okay, the area of the ith semicircle, now remember this has a little delta x here, we don't forget, Ripley, to put your delta x on, is going to be pi, let's just take the constant out, it's pi halves. Now what's my radius? Well, the distance from here to here is my diameter. Okay, is my diameter. So I got to take half of that. And we know from the previous problem that that's going to be 2x sub I minus x sub I squared. That's just that distance right there. I need to take half of that, and I need to square it. Right? See? Pi halves, that doesn't change, it's constant. The radius is half the distance between these two, half the height of the slice of action, if you think about it that way. Right? Take a half, and then this tells me to square it, and I'm done. Now v sub I. Now, right here, when these get complicated like this, because my brain goes, right here, I have a tendency to want to clean this up algebraically a little bit. 2 square, I'm not going to multiply this out, because I'm just setting up the integrals. But I can deal with constants, right? 2 squared is 4, times 2 is 8. So this is going to be pi 8ths times 2x sub I minus x sub I squared. This is still squared. The reason that 2 disappeared is because I squared it and then pulled it out. That's where I got this pi 8ths. And then times delta x. Nothing to it. And then last but not least, we write the actual volume. Watch how easy this is. Pi 8ths, integral from 0 to 2 of 2x minus x squared. That whole thing is squared because we squared our r up here. And dx. And I'm done. All right, now I'm going to make it a little easier on myself. I'm gonna erase up here, and we'll do triangles, and I'll do these in some obnoxious color, probably green. I hate that color for some reason, but it's cool. I'm going to do right triangle, right isosceles triangle, and I'm going to be lazy as heck when I write this out. Right isos triangle with side in the region. It's just going to be easier and faster, which I'm sure you guys are ready for. Now think about this. A right isosceles triangle just means it's a right triangle where both the sides are the same length. So I'm going to take a side, I'm going to stick it, let's draw ourselves a slice of action over here. One of these sides is now in the region, and then the triangle comes out like this. That's a little bit too far. Whoops, whoa, fumble. A little bit too far, even at my scale. And then my triangle is coming out at me. Kind of looks like a tooth, right? And then my right angle is right there. Okay, so again, let's start it the same way. Area of a triangle is 1/2 base times height, which we know in this case, because it's a right isosceles triangle, it's just going to be 1/2 base squared, right? Now you're probably already saying, well, Ripley, shouldn't it, since it's shouldn't it be half of this volume? I don't know. Let's figure it out. I've got a sub I is equal to, ooh, you guys got to yell at me, delta x, because that tells me everything, doesn't it? A sub I is going to be 1/2. I know the base is going to be 2x sub I minus x sub I squared, right? So that's this guy, but then I have to square this. Hey, it is working out the same way, isn't it? So volume sub I is going to be 1/2, which is intuitive. I know it's not rocket science. X sub I squared times delta x, and then the overall volume is going to be the integral. We'll pull the half out in front. I'll just leave it in because I didn't give myself enough room. Integral from 0 to 2 of 1/2. That's supposed to be an x. Why did I get a pi? That was weird. I just had like a circle flash go through my head over here. That's crazy. So that is an x. Jeez Louise. And this is going to be 2x minus x squared. Square the whole thing, and that sucker turns into a dx. That's it. They're not hard. They're actually pretty fun, but the problem is you're going to have a head shift between volumes by rotation and volumes by cross-section. The key is, the thing that's going to tell you what you're doing is this right here. You're going to hear the word, you're going to read the word cross-section. You're going to have that thing in your brain. So when you see or hear that, you got to do a head change. All right. In the next lesson, I'm not going to do it right now. In the next lesson, we're going to talk about shells. I've already mentioned shells a few times in this lesson. Shells is a trip. Shells is fun. And it's very useful for a number of reasons. But we're not going to go into it in this lesson right now. I'll meet you over in the next lesson. All right? Have a